All right. Well, thanks, guys. Thanks, guys, for showing up, of the people who were able to in this crazy, crazy time. My name's David Liu, and this is something I've been wanting to teach for a while. I get a lot of questions about how to design mobile power systems that are meant for overland or camping vehicles. I get a lot of questions about batteries and solar, so I'm really excited to be able to talk to you guys about this subject. Oh, come on. All right. So first things first, batteries and the vehicle electrical systems are inherently dangerous. So just be very, very careful with dealing with any types of the electrical systems that are in vehicles. For the batteries, be very, very careful of them that are like some of the ones I'll be showing today. They can kill you very easily, or they can give you severe burns. So be very, very careful. If in doubt, get an installer or another licensed professional to help you with it or do it for you. There's no governing body right now that does this type of work, so just be very cognizant that there can be a lot of misinformation out there, and that we don't really have a defined standard. So a lot of this is kind of based upon applications notes that were created by some of the vendors for the parts that I was using. So just know that for your own risk. All right, with that out of the way, I'm also like to do special thanks out to the people who actually helped make this presentation or I learned from. So Matt Santora was one of the people that I came back when I was coming back through with my truck when I had purchased it in Joshua Tree. I met him, and he does installs and he does some of the system creations. You'll see some of the photos from his van today. Travis O'Neill is one of my friends. He's a guide out in Las Vegas, a climbing guide. And he also has a transit van of sorts. And so we'll be talking a little bit about how he designed his, because his is solar only. I got to pick his brain about some of the subjects before I started my build. And Precision Camera for hosting this event. I've been shopping with them since 2007, so there's a lot of cool crossovers, especially with traveling photographers in video, and some of the overland crew that likes to do photo and video. This is of relatively useful information. Okay, so a little bit of the motivation. Why the heck did I start doing this to begin with? Well, it really started from a 4-week trip that I have from work. Every 4 years we get a work sabbatical, and I wanted to travel across the US, kind of camp out of my car, do some of the national park touring that I've been wanting to do since I was a child. And I felt like that would be a great opportunity to kind of learn some of those technologies and and be able to record some of my adventures with the camera like I'm recording now, and with other types of instruments that I had, such as a laptop with me. I had an iPad with me. So making sure that those had power were of also great interest. And because this was a longer trip, I wanted to make sure that I had power for other extended things, potentially a fridge. So that really came into the mindset of when I was trying to create this adventure vehicle, which I purchased. So actually here in this photo, that's my truck. That's actually Matt's van. This is where we met in Joshua Tree randomly. And yeah, that's me bringing that truck back to use for this particular adventure. So that's what I really set out starting with when trying to learn all this information and gather the necessary items to make this presentation, and also to make that system that's actually in my truck right now. And so, I had a lot of inspirations. The Transit and Sprinter builds where, you have great space, you have tons of really cool electronics all in there. I've seen a lot of amazing builds that people have done, especially traveling photographers have some of the most elaborate setups that you've probably ever seen. So that's one thing that I had a really big inspiration when trying to make my system is what lessons can I learn from theirs. And ultimately I came down to this one question: how do you really translate it to a specific vehicle setup? Everybody's vehicle is different, all of their needs are different. How do you make a system that actually makes sense for the given need that you have, right? And that question kept percolating. Now, on that question of secondary power, I started thinking about, what things would I really need it for? Well, the things that you would use to use during your trip to record your adventure or to look up logistics, any of that, right? So you're going to be dealing with cameras, laptops, phones, drones, maybe you have a GPS unit that you need powered. All of those things require power if you're not moving, especially if the car isn't available to be, to charge your system. So that secondary battery system then lends itself to charging your other accessories. It can also power some of the nice-to-have accessories. So you have fridges, lights, water pumps, all sorts of things where that secondary power system can give you auxiliary capabilities that normally aren't available. And then the third part is, it's nice to have secondary power all without having to keep the car on and drain the battery, right? Or if you're stationary, not drain the battery. I've seen multiple camping trips where people have just, turned the car on, charged, and then we have to jump their car in the morning, or they're many, many miles out and have to ask for somebody to drive in with a jump pack and jump their car. So, we've all been there. I didn't want to have that problem, and that was another consideration around designing these types of systems. And actually, in this photo, this is over at Overland Expo. So I actually got to go to Overland Expo during my trip, and you can actually see the photo of the P-Core system here by Patriot, and then some of the stuff that they use. And we'll be talking a little bit about why it's configured in that manner with the way that they have it. All right, here's all the things we're going to be talking about today. So we're going to be talking about designing specific to your vehicle platform and usage. We're going to be talking about the different types of case studies that you can have, and a design decision tree on how you would choose what type of system and what type of configuration you would have. We're going to go over some of the basics of the things that you probably should at least have a basic understanding about or learn about if you want to start designing your own system. We're going to go over the different types of battery formulations and when you would use which one over another. And we're also going to talk about some of the specific charge systems, the AC DC splits of like when you would actually use which type of system, how you design around it. A little bit more about the wiring layout and how you would design, from a schematic level all the way out to how you would actually put it into an enclosure to put into your vehicle, and how you do the final build and assembly. And I think the first thing that I found really, really early is that there's no real way to design one system that works for everybody, right? I think that's one of the things that ultimately we have to acknowledge here. What works for one person is probably not going to work for another. What works for one vehicle may not work for another. What if your needs are different, right? Those all start changing how your system is designed. So these are just a little bit of the splits as to what type of things are taken into consideration when you're designing a system for yourself. Heck, even between one vehicle and another of your own ownership may change. One vehicle may be outfitted differently than another. And these are the types of things that you want to consider when designing your system. And I know I've put a lot of elements up there, but what that really means is that every one of these items really has to be thought out in your thought process when designing. Like your usage, what accessories are you powering, how much space do you have, how much roof space do you have for solar, how often are you moving, all of that starts to change it. And that's ultimately, when you come to a good system design, is something that is quite important that you have to really jog your mind and think about before setting out and building your own system. And so the easiest way, in my opinion, is to actually design the system and work backwards from your usage. So what I mean by that is to take all the accessories that you would want to use, understand what their requirements are and how often you would need it, and then design your system around that. And that solves a lot of problems because then you won't over or under build your system. You can overbuild a system, right? You can definitely underbuild a system. We know a lot of people who have underbuilt systems. I see very few people overbuilding a system, but I see a lot of people underbuilding a system, right? So in order to make sure that you don't buy too much of what you don't need and accurately size your system correctly, this is one of the things that I would recommend, and I'll go into that right now. So when we're talking about the design process, right, if we take a look at the different type of platforms that your system is going to go in, it's going to be split among a few different areas. You're going to have, and a good example would be you're going to have a truck on one, you're going to have a van on another, you're going to have an SUV, right? So let's take a look at some of these examples here. For the truck, say it has a usage of 30 amp hours per day. You want to use both systems. This is basically my system, right? mounting location, I want it over the rear, I want it inside the rear shell, so I can't, there's certain requirements that make it so that I can't use a lead acid battery. Well, that's an example of one. Now we go to a second example of a van. So van, you have a lot more space. You also start using a lot more stuff because you can pack in a lot more accessories. So the types of usage requirements go up in that situation, but you can also mount it on the interior. But it does take up your interior space, right? And that's something you do have to worry about. The third one, another good example of this when you look at the design process. Well, what if you're in an SUV and you want all that interior space? How do you design a system that doesn't have it on the interior of your car? Well, if you look at a lot of SUVs, they usually have enough space for a secondary battery. So you can use that space to actually put in a system, but then you have to know the limitations of that, but also the advantages, right? The advantage is you're not taking up space. The difficulty is it's hard to get that much charge inside a space that's limited to maybe just 1 or 2 batteries tops, right? But if you know your usage is below it, it can work perfectly and not take up space in your vehicle. And this is actually an install that one of my friends did in their SUV, where they actually used a lead acid battery as a dual battery system. Works for them, right? And note that all of these systems have conflicting requirements, right? You don't have, the truck is the same as the SUV, right? They have conflicting requirements, like mine's on the inside. The SUV has to worry about space. I don't have to worry about space, so I can have it, right? So there's these considerations when you're designing your system about what you are going to care about and how that's going to ultimately affect your system. So when we look at the implications of what some of these requirements become for the truck in this case, well, being on the inside, you don't really want to have that battery next to you because it can off gas. It's not really good for you. It's dangerous. So the lead acid, AGM, any of those I don't really want that on the inside. So my battery formulation's already changed in that case. The charge requirements for what I wanted in that particular truck mean that it needs both alternator and solar. So then I have to account for how I'm going to design it and put it in there. For the van, if for this particular build, they only wanted solar, but they have a lot of roof space, so they can actually have that system, right? So that you can see how those requirements are trickling down into the designs. The SUV is very similar, where the install location means that I can only have lead acid or AGM or those style of batteries that are meant for the engine bay, because that's where I'm putting it, in the engine bay, right? Well, then I'm looking at an alternator or dual charge system. So now every one of those elements has started creating and shaping the system that I'm ultimately going to put into my my vehicle. All right, here's the fun one. Badly drawn in Google Slides, right? But let's start from here, right? This is kind of a design decision tree based upon usage. Remember what I was talking about, knowing your usage. We'll go over how to actually calculate your usage in just a sec. But one of the things that you're going to want to see here is you're going to start from what your total amp hour usage is. You're going to say, how much am I actually having, right? If I'm less than 15 amp hours, if you do the calculation on like the off-the-shelf systems that you can buy at, I don't know, REI or online, right? Most of those are below 15 amp hours. So if you're using less than that, an off-the-shelf solution isn't bad. It's going to save you a ton of engineering time and a lot of testing and dangerous stuff that you don't want to be doing, right? So it's not bad to use a battery bank. Like even like the battery bank that's powering that GoPro that's sitting right there. It's not bad if you just design it to set up all your lights to use that run off USB. That can also work, right? It's not an incorrect system. It's just spec'd out enough for what you do. So when I go camping in a tent, I'm not going to carry a big battery. I'm going to carry stuff that can run off of a little battery bank, right? So those types of scaling problems, you really have to think about what is your usage and how do I design around that usage. So if we start going down where you might start thinking about it, like maybe the 15 to 50 amp hour range, then it's going to be then broken up by your battery location, right? How much space do you have inside your car? Where's this battery going to be? I think that's one question that a lot of people get stumped on. They go, well, I don't know where it is. I'm like, you should really think about where you want to put it, because that heavily influences whatever design you have, right? Because if it's on the inside of the engine bay, really that's a lead acid, and then you start, so now your design constraints have already shaped and put into one area, then comes the question, do you need solar? Because then it'll either drop into a battery isolator or a dual charge system, or a dual charge system with the capability of doing solar. So that's what that left side is. Now, if we start going to the place where it's outside of the engine bay, you start getting a completely different set of design constraints, right? In this case, it then pivots upon, do you need solar, right? Solar, if you don't need solar, there's systems that you can design that use these other types of charger controllers. We'll get into what some of those are. But it basically gives you, an off-the-shelf solution. If you don't need solar, you can essentially use the same thing, like a DC to DC charge controller, and that's what that side is. If you are doing solar only, right? There's a lot of systems that do that. Like there's, Victron stuff. There's all types of companies that make solar only systems, right? And that's a great place, because then you don't have to worry about integrating it into the car that much. You just hook up a solar panel, hook up the battery, hook up your accessories, be done with it, right? So any of the MPPT charge controllers will work, and that's max power point tracking. If I'll talk about that in a bit. And then if you need kind of the everything, the kitchen sink, which is what a lot of people are really wanting right now, then you're going to have either like a red arc system or a split system with a selectable charge direction, and it's probably going to be, so most of these are probably going to be lithium or similar. It doesn't have to be, but you're going to be dealing with the battery inside wherever you're at, so that might be a bit of a consideration as to what you eventually choose. Now, I say from 50 to about 500 amp hours, mostly because if you choose enough lithium iron phosphate batteries, they kind of fill up the space in a van. I've only seen maybe 500 amp hours before the alternator is going to have trouble charging it anyways. You have to have 2 alternators, and it's just blah. And really anything past that point, you need a big enough vehicle or an RV or something else to carry that. And now there's a notable exception. So there are, if you have an off-road capable trailer, that equation can change, because then your battery, you can actually have a lead acid in the back of that guy because you're not in there, right? It's technically out in the elements. So there's some external considerations. And really anything past that point, you should really be using a generator just because you're not going to be able to charge it in time, right? And we'll go over the calculation of why that actually works, why that number is the way it is, right? Okay. So all of those on the design tree, we're focused on your usage and your usage requirements for your power system. So getting the right amount from your power system is quite important. And what you're going to be doing here is gathering the numbers for all your devices, calculating their amp draw and what voltage they're at. They should really be at 12 volts. If they're not at 12 volts and you're designing a 12-volt native system, there's a bit of a problem. But you're going to be looking at what is the max and what is the average. Because when something kicks on, so example, a fridge will kick on and it'll have a huge current spike when it kicks on, but then its average is low, right? So those are the things that you have to think about, because that will start affecting your wire gauge and how everything's split. So just be very careful about that. All right. And the way you're going to do that is by calculating for amp hours. And if you have a wattage, then make sure you back convert it to amp hours to make sure. So it's 120 watts at 12 volts. Well, P equals IV. We'll go into some of those equations, right? You can then get the current that's coming out of it, and then you do that current about how long you're running that device. For a fridge, it's 24/7. For a light, maybe I'm only holding it for 2 hours, so do it upon amp hours. And that's a really easy number. That's kind of one of the few standards that actually exists in this space, is them talking about usage requirements and that will translate to your battery size, because then all the batteries have amp hour ratings, and that's why it's a bit important to know that number. So as an example, we'll look at a few things here. So the lights, so I have about one 1 watt at 12 volts, right? So it's about 0.3 amp hours. My fridge is 0.75 amps, so it's 0.75 amp hours, right? My pump is 3 amp pull, so it's 3, if I use that pump for a full hour, it's 3 amp hours, right? So you're going to do the current and the time, and that's going to give you how much that is. So it's additive, right? So then, I'm using 0.75 amps for 3 hours, and it's just additive at that point, because that's how much you're using over time. And that's the way you're going to do your, the curve of the battery depletion of how much you're using, okay? And that's what I'm saying here. So convert that number then to how long you're using them. So if I need 5 hours at 0.383 amps, then I'm going to have 4.15 amp hours, right? If 24 hours of fridge, I'm going to use 18 amp hours, based upon their number. Now you have to measure. This is also another part. If you're unsure, measure it. That should give you a better delineation of how much it's actually using. The pump, I'm not going to cycle that pump 24/7, but I am going to use it when I'm going to pump water, right? So it's 0.5, maybe 30 minutes essentially, right? But at 3 amps, well, that's 1.5 amp hours. So all of those, when added up, tell you your usage requirements for the given time period that you're talking about. And that number is very important because remember that design decision tree, every one of those is going to define out which one you're going to be using based upon your usage. And so in this case, my total will be about 24 amp hours. So this is actually the calculation that I did for my truck, because that's how much I think I would be using. Now, that some of that did change. Some of it was more and some of it was less. But we'll go into that when we get to the final part. And note that all of these are native 12 volt devices. So the lights run off of 12 volts. Everything is native 12 volts that I'm showing you here. If something doesn't or something runs off AC, then you got to do the calculation, and then there's efficiency loss, things that you do have to consider. And we'll talk about why you generally want to keep a native 12 volt system when you're designing when you're trying to build your system. And again, we'll talk the max ratings. Those will also help later when we start sizing the wires and all the other components and fuses when we get into that. So let's go over some of the basics. I would suggest that you write these down and go explore and go understand how these actually work. These are very, very basic. We're just talking about wattage, amperage, Ohm's law, things that are relatively useful when doing calculations, or you have to convert from one to the other. Or you have to do wire sizing. All of this will start to matter. So you have Ohm's law V equals IR. So there's different ways that you can configure that equation with its relation. One's inverse over each other. Understanding how that starts affecting your system size, and then you can convert that equation into a power equation, which is P equals IV. So power equals current times voltage. Right? And then there's another transform, which you can say power equals current squared times resistance. So if you know those numbers, you can start doing replacements and you can basically use those equations to try to help understand your wiring needs, your fuse needs, and trying to interchange between different types of specs. Some other concepts that are of great usage to know, understanding the concepts of series and parallel. This is very important, especially because we're dealing with current, or even if you're dealing with voltages on your solar panels, understanding there's some danger if you try to connect a bunch of them in series, you really want them in parallel. There's considerations that you must understand as you are doing this. RMS, root mean square, really useful in certain types of power equations when you're dealing with rectification. Kind of important when you're working with inverters. It depends on the inverter type. I think with some of the newer inverters that are really high efficiency is less of a problem, but the old school ones definitely had this issue. You're also going to worry about the inverter efficiency curve. So some inverters are only efficient at certain levels, and then they'll be out of their efficiency range past other places. So this is why I say dealing with AC adds a whole nother level of complexity that generally I don't like dealing with. So just be cognizant of that. DC to DC conversion. So, the battery coming out and the way it's charging is actually two different things. A DC to DC charge will actually can take different types of varying voltage and try to put it at the correct charge rate for the battery. And you'll see this in solar systems, right? That's one of the big takeaways that solar systems are actually doing for you, is trying to create the right voltage to charge the said system at the right voltage. Joule heating is going to matter in wire sizing, and then maximum power point tracking. That's part of that, what I'm talking about with the DC to DC, but that's specific to solar. And it's basically using the right voltage and current conversion to lessen the heat loss when sending the power over to the battery. I would say just get an understanding of what these are. Even for some of the basic terminology, you might see this, at least in some of the documentation. Hence why I said it's probably good to at least review a little bit of this, just to get a basic understanding of this while you're designing a system. Wattage and amperage are probably the two things that people are going to care about, because they're going to change your wire gauge that your system is connected with, and they're going to also affect the battery sizing that you're going to deal with. And so you'll need to convert back and forth between amperage, wattage, and just understanding what some of the stuff that I did before on taking wattage and converting it to amp hours based upon the usage. That might be required, because sometimes you'll get a device that says it's this wattage. Well, you're like, what's the amp hour rating? How much am I using? And then you have to go back calculate and figure out and make sure that you are accommodating the right amount of power in your system. And I think that's kind of an annoying part, but you're going to see a lot of the documentation that'll have it in all sorts of different units and everything. You're just going to have to convert back and forth or physically test it. And if you normalize all of them to the same value, it's a lot easier to size your system correctly. So why don't we drop into the topic of batteries? So batteries are highly confusing, because there's this big argument of the different types of batteries, this, that. Really, the argument should be, where are you placing the battery? Okay, pick the right battery for the job, right? And so there's a bunch of different battery types, right? We have the flooded wet lead acid batteries that are normally used in vehicles, AGM if you have the sealed lead acid type of systems. There's also gel cells. You have standard lithium ions, the ones that like to go on fire. And then you have lithium iron phosphate, which is kind of a new style of battery that's come out recently that trades off some of the power density for thermal capabilities. And then there's also quite a difference between cranking and deep cycle batteries. So the crank batteries are made to dump tons of charge when you crank that car. The deep cycle is meant for a different type of charge cycle. So just understand that if you are using them, that they're going to have very different properties when they charge and when they discharge. So lead acid batteries, they're the king of versatility, availability, and cost. On your trip, anywhere, you go by some auto repair or a retailer, you're going to be able to find a battery, right? Very, very easy. If one dies, you'd be like, well, no, I got another one. I have another battery now, right? Easy to service in the field, at least if you have roads and some basic civilization, okay? They're meant for rough environments that can handle the engine bay and the environment of the engine bay. That's key if you need the space, right? If you need the space inside your vehicle, so you're an SUV or something that's much smaller, you're gonna want that space. The sealed lead acid or a standard lead acid or whatever different type of formulations I showed before will be a great choice, because it can handle the heat of the engine bay, and that's why they're very popular as a dual battery system in a lot of overland vehicles. It's also meant for a lot of rough environments. Like you see marine capable ones, so the marine batteries are a favorite because of that. They can handle a lot more weird stuff, like if we start driving our car into standing water, which we've probably done a few times, right? So those are the things that you should really be considering. And there's a lot of different variants of lead acid for slightly different purposes. I talked about a few, right? There's marine, there's cranking, there's deep cycle. They all have differences that you should try to understand before you choose one, but understand that they also are all roughly in the same bucket. Okay, and remember the non-sealed versions off-gas hydrogen. This is when you jump. This is why when you jump a car, right? They say to not connect the negative lead once the second negative lead to the other terminal, because if that thing arcs, you'll have exploding hydrogen. That's why they say put the second part of that lead on the chassis, because then you're not arcing directly across the battery and having a spark. Okay, and it's certainly not a good idea to have a lead acid battery in the interior with you because it off gases and all sorts of stuff, right? I think one of the main things that people don't understand is that lead acid batteries are not made to be used past 50% of their capacity, because the voltage curve starts just dropping tremendously. It'll go below like 10 volts once you use it past 50%. So really, if you have one battery, I would take its amp hour rating and cut it in half. And that's generally what the consensus among many of the people who design these is, that you really only have, if you have a 100 amp hour lead acid battery, it's really just 50, okay, that you have usable. And it's also not a good practice to discharge it past 50%, starts damaging the battery. I'm sure, many of us with our cars, we've seen some of the elements. You have a car that won't start, you have accessories that are constantly draining it. We've all ran into this problem, or if you've been in, at least you've witnessed this problem by other people. And another part is the charge rate is, there's a specific charge rate called the C rate, and it should be less than 25% of the battery's capacity. So if it's like 100 amp hours, it should be less than 25 amps that you're charging it, because it can damage some of the cells, and there's like different types of specs that you can go look up for the batteries. It's called C rate if you really want to figure it out. But just know that that's something that you have to consider when sizing the system. Lithium batteries, let's talk about those. There's the ones that are used in the battery banks. There's ones used in our phone. Those are lithium ion ones. They have some scary thermal properties if you use them at their limit. They can go on fire. But they have high amounts of charge density. So like our laptops, our other devices, they lithium ion, super light, tons of charge in one of those batteries. There's a new formulation that's starting to become more popular, which is lithium iron phosphate. And that one, it's a lot heavier, less charge density, but has better thermal properties. Does not heat up as much, is less, has a little more tolerance to charge temperatures. Still can't go in an engine bay, or at least I wouldn't recommend it. I mean, I have seen people do it, but I just really wouldn't recommend it. And has more temperature stability and less fire problems, right?
What is the caution with regards to engine bay environment for that specific battery type?
Damaging the cells. So that's
temperature, contamination.
I think it's temperature. It's more temperature. Like the high heat is the bigger problem that you have to worry about. This is generally why they say you shouldn't, you can have it as a replacement for your starter battery, but if your starter battery is in a very hot place and it's not like in the back of your trunk like BMWs are, that's a bit of a problem, because those high temperatures are going to start affecting that battery. Most batteries don't like a lot of heat. I don't think any real battery formulations like that, regardless. The big issue with lithium batteries is they're expensive. And lithium iron phosphate is no joke expensive. It's used for the 100 amp hour battery, like the one that I have, it's $1,000, right? You want 500 amp hours? Well, you need 5 of them. That's $5,000, right? So it's expensive comparably, when you can use a $100 or $200 equivalent amp hour rating, or if you want the actual full amp hours, then be like 200 or something, right? So those are the things that you would have to consider when doing a system like that. It's a huge amount of your capital that you're investing into a system just in the battery. So do you really need it? Do you need a smaller one? Can you get away with another system? Really know your needs. This is why I say know your needs, because it can get really expensive if you go down the wrong track of the design tree. All right. Some notable differences about this type of battery formulation. it can charge at a full almost 40 amps. So every day I can, while I'm driving, I look at it, I'm like, holy crap, it is dumping just tons of charge in there. And it can discharge up to 80 amps continuous before the battery management shuts itself off as thermal, right? So it can dump tons of current. So, I was running some very large devices off an inverter. So then, you're starting to stack a lot of current at that point, and it was supplying it no problem, 1,500 watts, no problem. And I'm like, okay, this guy is insane. I have a ham radio, HF rig. This sucker powered 100 watts while we were transmitting. No problem. Didn't skip a beat, right? And that's just incredible in my opinion. It does require the use of a battery management system. So those batteries will typically have on the top of them, they'll have their own battery management so that you don't, it'll shut itself off or it'll control the amount of charge that's coming in. You really want those with those batteries. Having just the pure cells is a little bit dangerous. They have a longer lifespan if you use them appropriately, 3,000 to 5,000 cycles. And cycling is like complete charge and discharge. Generally, I don't use more than half, and that prevents it from fully cycling, and it'll keep the battery health a lot longer. So just FYI, that's why generally you want to know the usage of your system and design it such that you never use more than 50%. Because if you use more than 50%, you start doing hard cycles on your battery. And it has very good discharge rate behavior. So up until like its last 10%, it's at 12 volts pretty much, or close to it, up until it ends. Whereas another battery, sorry, I'm drawing it the other way. So it's like this, and then it goes down. Whereas a lead acid starts kind of doing this. And you can look at the discharge rate graphs. Again, different batteries, different formulations, different cost. Just something to consider. Now we get to the question of battery choice. So the choice should really be dictated by battery location. And I've said this multiple times probably in this presentation. Maybe I've broken record already by now. Really should be based upon the requirements of what you're doing with it. So I've seen a lot of successful systems with just a single car battery. Like we just added a secondary car battery into the engine bay. Great, worked great, right? They didn't overuse what it had. We did the requirements, worked great. I've seen, and you can do it without the cost of that entire lithium system and all of the annoyances that come with designing a system like that, right? So sometimes keeping it simple is relatively useful, and knowing what your needs are, very important. And I've talked a little bit about not putting lead acids where you shouldn't and where you shouldn't put the lithium batteries, so I think we can probably skip that. And that's why I say, especially if all else fails and you just don't know and your needs are low, like an off-the-shelf system is great. It's fine. Like you don't have to have something that's that particular. Just find an off-the-shelf conventional solution that another company's designed and just be okay with using that. And I've talked about budgeting more than you need to make sure that you reduce the full cycles on your battery system. Usually the 50%, you don't want to be using more than 50%. Okay, so now let's talk about managing AC and DC, okay? So I would almost always recommend you design the system around 12 volt. Mostly for simplicity's sake. It's a lot easier to design when the entire system's running off 12. If you start having the need for 110, so like an example is this laptop that's sitting right here is not one of the new MacBook Pros. This one still has an AC charge adapter. That's what I'd use it for on my journey, okay? You do need, if you are gonna use an inverter, make sure, and it's with electronics, that you are using one that's a pure sine. And if it's not a pure sine, then this is what it looks like. And it's just this weird stair step. And that's really bad for electronics, especially fine electronics. It's fine with the resistive load, but if you have anything that's not like just a pure heater, absolutely get a pure sine wave inverter because it'll just destroy the power bricks otherwise. So just something to consider. Especially with an inverter, you have to understand that there's inverter power losses. You will lose a certain amount of power depending on the quality of the inverter, the type, and if you're in the efficiency curve of that inverter. I would always recommend a master kill switch because it does have for the inverter, mostly because it does have parasitic draw on some of the medium to low end models. It's also good because if you need to operate on the battery, it's relatively easy. So just remember that when you're designing your system and you have an inverter. And you can almost get everything 12 volt these days. You can get water pumps, you can get fridges, you can get fans that all operate off 12 volt. It's really, really nice. I mean, it's just look for the spec, look for any stuff on Amazon and other places that are 12 volt. Really, really easy to design your system. And I've talked about the importance of the pure sine wave inverter, and that jagged nature is just really, really bad for electronics like a computer. I would also say the other useful part about having everything 12 volt and also knowing which sections and how much the draws are is you could design the type of wire sizes and the fuses needed. So you can fuse them smartly. So if I've grouped, like the water pump on its own is going to have a certain rating, I can get and design them such that the fuse ratings are within reason. Like it's not too close to one end or too far below something, and won't catch if something gets a short or blows a fuse that I've destroyed something. So you really want to understand your needs there, and the advantage of keeping everything native, it's a lot easier to design the fuse ratings, and you can organize things a lot easier if they're all basically the same native voltage. All right, the meat of the presentation. All right, the solar and charge systems, the stuff that everybody asks about, okay? Probably the biggest subject and the thing that I always get messaged upon for expertise. Solar and charge systems, they've advanced a lot in the last few years, and there's a lot more solutions today that are meant for camping and overlanding than there used to be. And that's giving a lot of flexibility in a lot of the designs today, including the build that I did is a great example. And when you're designing the solar and alternator-based charging, then that is also subject to your use case, right? Your vehicle, how much roof space do you have? Do you really need solar? How much amperage can your alternator give? All of these start coming into consideration when you're designing for a solar and a charge system. For solar systems, there's three main panels that you're going to see. You're going to see a monocrystalline, which is, from what I understand, is the most expensive but best performance. It's also probably the most common. Polycrystalline is cheaper to produce, has a little bit less performance, a little less heat tolerance. And then there's film amorphous. The film amorphous is a little bit hard to get in the United States. It's very popular in Australia. For like the big mats that you can put out. Stuff's very flexible. Most adaptability, it's flexible, but it also has a short lifespan, so that's another thing to consider with that type of panel. And if we were to split the charge systems into three areas, you have three main types of charging that you're going to see with this. You're going to have a solar-only system, so like an MPPT or PWM or pulse width modulation is going to be one type of system that's a solar-only. Then you're going to have an alternator-based charge, which is a DC to DC charging of some sort, right? So that's another form. And then you also have dual battery. Dual battery is its own specialty because it's not doing a voltage change. You're using your alternator to charge the second battery. You're not transforming its voltage to charge a different style of battery, and there's no separation, right? And then you have dual alternator and solar, and that's like, kitchen sink, you have everything. And then there's just an off-the-shelf system, which might even have more or less. Again, there's lots of systems that are meant for different types of use cases. So when it comes to solar panels, there's really two types that should be considered. There's rigid and there's flexible. So rigid, it's really easy to find 100 to 400 watt configurations. You can just buy them really easily online. They're more difficult to mount because you usually have to have like a flat surface to mount them to and some type of drill and rig it, and it's not too heavy, but it still is kind of a pain in the butt if you don't have a rack system on the top of your car. Flexible, you can also get those. Just understand that they'll be less efficient because there's no cooling beneath it. You'll notice that the hard panels for solar are offset. There's a gap beneath them to allow for airflow because they're not in their efficiency range otherwise. I've seen people mount them on skyboxes. I've seen them mount them on hoods, but that's hot. So it works kind of, especially if you're not moving, it works, right? If you're moving, then it could heat up pretty hard. Then there's the fold out ones. So like there's like the Red Arc ones that you see are the other, I forgot what other brands that have it, but you know, they have ones that fold out and you can put over the hood of your car or you can put on the ground. Those are generally film amorphous. Those are like really resistant to bending and like impact, and they generally hold up like that better than some of the other ones, but they don't last as long. Yeah, it's kind of okay. Well, sorry. And so it's generally less efficient, but it does have some advantages like being able to be put into like a blanket format. So when you're stationary, you can just throw it out on your car. Still, I have a hard time getting them in the US. So, I mean, that's why I don't design my systems around them. But that's the advantage of the standard plug for solars. You can change depending on what your needs are. And I've talked a little bit about this, about the cooling factor, but the other part that's also important is the tilt. And if your panel isn't able to tilt, then you're not going to be in the maximum range to be orthogonal to the sun's rays. And so you're going to get a huge efficiency issue when it comes to actually getting the most out of the sun. Because the sun doesn't just stay in one place. It like tracks this way, right? So if your panel isn't at least capable of tracking, you can't just like, put it up and angle it. That's a bit of a problem because you're not going to get the most charge out of it. If you're using a dual system where you're not solar only, then that might be fine. But if you are solar only, you definitely want to think about how you can position the panel to get the most out of the sun. Okay, I would really try to also size the wire gauges correctly for the panels. Generally, if it's anything more than 10 feet, I'd go 10 gauge immediately, or a higher gauge, which is a lower number. So that's one thing to consider. Another part to consider is that if you have multiple panels, generally you want them in parallel. And why that's important is a lot of those connectors are only rated for a certain voltage. And if you put a bunch of them in series, they're going to add voltage instead of adding current, right? So you can go over the spec and you can have arcing problems and you're not in the efficiency range. So really try to understand that most panels are going to be better in parallel. There are some situations where you want it in series, but it depends. Keyword, it depends. But just, yeah. What's up?
I'm familiar with MC4 connector panel.
Mm-hmm.
Something that I've been seeing a little bit more here lately, there's a company called Furrion. I'm not sure I'm pronouncing it correctly. And it is a 2-pin connector, and they have a family of weather-covered bulkhead connectors
Right.
that make it convenient when you're not going panel to panel.
Right.
And is there something going on in the way of either prevalence or standardization as far as these connectors are concerned? My primary familiarity with MC4s has to do with permanent mounted systems.
MC4 is the easiest. I think that's the problem is MC4 is the easiest. There's so much availability of the MC4 connector and the accessories around it. I don't know, I think it's still the Wild West in the solar space, right? Like we still get a lot of these new connector specs and proprietary connectors and all these, but it really comes down to what is your DC to DC system able to handle. Like sometimes the actual unit for solar will tell you that it can't go over a certain voltage. Then that's your limitation of how many you can run in series.
Generally speaking,
Yeah.
years ago,
Mm-hmm.
hard-mounted systems, meaning permanent installations, put a high limit of 600 volts strength, maximum VOC. And one or two of the last systems, while it was still active in this field, was easily 3 times that much. Those high voltage systems would definitely get your attention as far as that's concerned. The MC4s were rated for 300 watts, 600 volts.
Yeah, the problem is a lot of the fuses that you would use typically in the marine space can't go up that high. So now your components are starting to limit,
Exactly.
right, your capabilities. And this is why I'm saying in this space, you do have to worry. Just know that it's there.
My curiosity has to do with one or the other choices simply because of the fact that, going back to the top of the paragraph, MC4s need a special tool for disconnections. Put them together and they stay together.
Yeah, it's hard to get them apart. You had to get creative on getting them apart.
There's actually a special tool.
There's a special tool, yeah.
Okay.
But I would say we can take that probably to the end of the presentation. But I would still say for those type of situations, the space is still very new in that regard in terms of what's the best for at least the usage that we have in overlanding or camping. So that part I'm still watching. I'm not particularly sure where they're going to go with it. So
Right.
we'll see where they go.
I think inherent to our activity
Yeah.
is the ability to set up and stow your system, especially if you go camp touring. In my particular taste is never the same place twice. If I'm out for a week, I might be in 6 different campsites.
Most people just use Anderson plugs at that point. So, and I'll have a picture of what that looks like. Yeah. So, like my friend's system, we designed with an Anderson plug. So we just it's up at the front of his bumper. We just hook it up, and it doesn't matter. But I'll show that now. So another thing, panels must be kept clean. Even mildly dirty panels can affect you by 20%. So probably every few days, I would go up and actually wipe down with like Windex or something my panels because I was in Moab. It's going to get dusty. You're going to have an efficiency loss. And I was seeing up to 20% decrease in efficiency just by a thin layer of dust. So again, if you're going to go solar, know that you have to keep those panels really clean and just have a daily routine around that part. Photo here. This is an example of a tilting solar system. I think this is, so this is Matt's. This is the van program here. And so that's about 400 watts of solar that can tilt. And so that gives him the maximum tracking. Mine is static. This is my truck. Mine can't actually move, but I also am charging through Alternator. But the only reason I have that panel is just to recharge, kind of trickle charge whatever's I've used, and that hasn't been charged through my Alternator. But that just gives you kind of an understanding of why we do that. And also notice that both of us still have enough space under, especially with mine, I have it directly over the rack, so you get tons of airflow as you're driving. So I was actually getting charge from the solar panel while I was driving because it was just located in such a good spot in its efficiency range. And here's an example of some of the charge systems. This is a dual battery isolator. This is an AC, it's a DC to DC charge system that's very high current. That can charge some really relatively large systems. Red Arc is another company that's very popular in the overlanding industry. These are nice because you can stick these in the engine bay. They can be in the engine bay or outside the engine bay. Renogy and other types of systems, that are meant for solar only. I see a lot of those in van setups because there's a lot of them that are running solar only, or like a mini house, like off-grid house. They'll be using one of these. Really cheap, runs solar, charges the battery, very simple, be done with it, right? That's what's really, really nice about those systems. And so these are an example of those types of 4 systems. And there's a lot of different companies, but these are the ones that I'm familiar with. I don't want to particularly give, one of them a calling, but these are the ones that I've designed systems around at the least. Dual battery isolators are useful just because they already use existing infrastructure in your car, right? The alternator. It's very easy. You have the alternator, you can hook up. This is how a dual battery system would work, right? You would actually have the auxiliary battery. This is your starting battery. That's the isolator. It charges through the alternator the same way your regular battery charges. When the car shuts off, it splits, and then it's its own area. It splits off to its own circuit. It's no longer connected to your starting battery. And the advantage of actually doing that is people will actually do this, but not actually have anything charging on the other side of that, on the overland vehicles, and just use this battery to jump this one if they need it. I've seen that many times in like the emergency vehicles. They'll actually have a dual battery system like that just for that case. just for another jump battery, which is kind of neat. Very quick install, allows for charging the battery where the alternator is running. One really easy if you have the space inside your engine bay for it. The next one, we're going to jump up to DC charging. The red arc is a great example. This is pulled directly from their documentation. It's different from the dual battery system because it takes in and does a DC to DC conversion of the voltage to attempt to get the best type of charging for the battery. So it has charge profiles for the type of battery you have. It also acts as an isolator. So it's kind of combined 2 or 3 items in one, and it can be adapted for different batteries. So I can use my start battery, pipe in the power from the alternator, and it can charge a lithium battery because it has the right charge profile. Both Red Arc and Sterling make products that do that. I think Red Arc can go up to 50. They just released a product that can go up to 50 amps of charging. The Sterling has like 60 amp plus one, so I've seen them in a bunch of Transit and Sprinter builds. If your car has regenerative braking, be very careful because you need a charge system that knows how to do that because it's taking power off the alternator. But if you have a smart alternator where it's charging on braking or it has some other type of smarts in it, it's going to go all sorts of wild and not be happy. So just know they do have certain models and certain settings that are made for that. Solar charge systems, I've talked about this a little bit before. There's PWM and MPPT. PWM is the old style ones. If you have an electrical engineering degree and you learn power systems, it was probably PWM for many years, and then MPPT became, it's getting a lot more efficiency out of it, but it's a little more expensive to produce. Its price started going down in the last 15 years, so you see a lot more MPPT usage than before. You'll still see both, but I would recommend if you're going to do solar, just get MPPT capable charge systems. The chargers are rated in the maximum amperage that it can charge. So you'll see something 40 or something 60. That's the most it can charge based upon the panels that are giving it to it. So just again, that's when you start getting into the sizing. Typically, base solar systems, if you just have a solar charger, are not really capable to be combined with a standard alternator charging because you have two sources of charge. And if you don't have a balance, like the Red Arc at least mixes the two, right? If you don't have something that can do that, then you're going to have it like doing back current, and that's super dangerous. So you'll see a lot of systems back in the day before Red Arc was available here that they actually have a physical switch that turns it alternator, solar only, and it's just they'll get to a campsite and then just turn it solar only and then go about their daily business. And typically a standalone system, if your car is stationary a lot, then you're really going to want a solar biased charge over an alternator based charge because you're not moving that often. So just know that's like, if you look at the time that you're staying in one place and it's a long time, then it doesn't matter how fast your car can charge it. If you're not moving, you're not moving. And then solar is going to probably be the preferred route. So when you come into system sizing, that's something that you want to be thinking about. Combining both is probably one of the newest capabilities that is become really popular in the last few years. My system does that. A lot of the newer technologies are meant around making that easy. And having both charge systems available means you get both the charge from driving and the charge from solar. So you both have moving and stationary capabilities of charging your batteries. And it solves a lot of the problem of the current backflow during dual source charging. If you have a single unit that does that can handle both and does good charge partitioning based upon what it is. And some of the newer units like the Red Arcs will actually have the built-in isolator, so it'll know when to just stop and not pull any more power, which is really cool. Also, just a note with the Red Arc, it needs to be connected to the actual starting battery for it to work. That's part of its logic. So just know that I wouldn't try to make it for a single solar-only system. With the Red Arcs, it has to be connected to a starting battery, so it's either alternator only or alternator and solar. Yeah, let's go. So when we go back to some good design considerations, we can go back and look at some of these, right? So My truck, I have solar and alternator, use about 40 amp hours per day max. It's in the shell. So the result is I designed it around a Red Arc DC to DC charger, lithium iron phosphate, 100 amp hour battery, and a 100 watt panel. For a van, and my friend's van, he didn't use much, battery in cabin. We just did a Renogy system, same battery, but a lot more wattage on the panels. So instead of charging off the car, he's charging more off the sun. SUV, another system that I helped create. We don't have photos of this one though. It's a dual battery, straight up dual battery, stuck in the isolator, dual battery, called it a day, and then just piped in some power. Okay, relatively easy. And here are some of the example builds. So this is my friend Travis's system. So you can see inside the van, you have lots of space. He has it in the spot where you can sit down. And it's relatively small with the lithium battery and all the wiring, and it's kind of compact on its own. What I do want to show you is this battery times 5 inside the van. This is Matt's system when he was building it out. This is what it ended up looking like. That's 500 amp hours worth of power. When you're in a van, you usually have a lot more accessories that use power. So again, you start scaling up the usages. For me, I'm in a tiny truck, very small space. I really only needed one because I couldn't even fit the amount of a water pump and everything else in there. Just not enough space, really. So this just gives you an idea of the types of different builds that you're going to see. This is pulled off the internet. This is, I think, from Red Arc. This is an example of them mounting one of the DC to DC units inside the engine bay with a secondary battery, right? So you can see 2 batteries here. This is just an image of Travis's system here inside the transit van with a battery. It works. It's not super organized, but it works. And sometimes that's all you need. When you need to get on your trip, you just need to build it and you need to go. But it works, right? And he did the homework at least to know which devices you need, and his is solar only. It doesn't have to have crazy big wires. You'll see my system that mine has crazy big wires because I charge at a crazy high rate compared to most people who have a solar only system. I do get this question a lot. How much solar energy can you get per day? Okay. The general consensus is per 100 watt panel, you're probably only going to get 24 to 30 amp hours per day, right? Because you have efficiency losses, there's only 8 hours a day you have sun. So 24 to 30 is pushing it per 100 watt panel. So in cloudier areas, like if you're up in the north, like we only got like 10 or 15 amp hours when I was up in Yellowstone per day. Just the sun was not out enough, wasn't giving enough energy to the panel. And it's generally recommended to have 1 panel per 100 watt battery, just like as you start stacking them. Mostly because the depletion rate versus the usage rate isn't supported. So that's generally the way that we would say to use it. How much vehicle charge can you get per day, right? If you drive about 30 minutes, with every day my morning commute, 30 minutes, I get about 15 to 25 amp hours out of my system because it can charge at the full 40 rate. But that's alternator, right? And it takes, if I were to charge it from a completely dead battery, it would take about 2.5 to 3 hours, the math comes out then, for 40 amps at, with some efficiency losses to charge this guy, that's about right. I've tested that once, but I haven't been stupid enough to leave my system on for too long. I think what happened there is I went on a plane and was out for like a week and left the car in the garage and forgot that, I don't have a solar panel hooked up at all. So it just depleted the battery with the fridge on. Worth charging AC, right? So what they mean is shore power. Is it really that useful, right? If you want to design a system that can do it, it's really hard. Most of them are not built to do it. There are some products by Red Arc that can do it. That's meant for trailers. I think it's called the Manager 30 that can do it, but it does have a lower amp rating. So just know that because of the long cable run. That's the reason it's designed like that. At the point you're in an RV park, I would just hook up to shore power. But the running joke is are you overlanding anyways if you're hooked up to shore power at the time, right? If you're, that's the problem that we end up having is how often are you going to use that system to do shore power, or is relying upon the other abilities more important to you? And that's one of the considerations that you have. Or if your system already comes with it, if it is a straight up like off-road trailer that has the charge, then by all means, like hook it up. But if you spend most of your time off-grid, then the shore power will be less of a concern. You just not have that eaten cost in your system design, okay? I get this question a lot too, which is, can I run an AC unit off solar and batteries only? Let me go through the math on this, because this one has been hotly debated for a long time, okay? So let's work a little bit backwards. You can take the best AC, which I've seen in most of my friends' vans, build at, which is a Dometic RV air conditioner. It's 1,670 watts at about, at 110 volt. Most of them are going to be AC. I don't really think there's a DC air conditioner. It's mostly all AC because of the way that air conditioners work. Assuming for 20% loss, just because you're not in its efficiency range, we're going to say it's about a total of 2,087 watts, okay? P equals IV, right? So then we can back calculate for the amount of amps required over that time. And then you do that upon how much you're using, how many amps and how many hours you're using it. So assuming 8 hours to make it through the night, I need about 1,384 amp hours to make it through the night, which is about 13 of the 100 amp hour batteries at $1,000 a piece. So that's $13,000 worth of batteries. Here's the other problem. How would you charge that system? You would need to sit in the sun for, if you had a 400 watt system at 120 amp hours per day. So if we calculate 30 amp hours per panel, you need to sit in the sun for 11 and a half days to get one night's worth of AC. This is the big argument for shore power, actually, which is like RVs, just like hook up, run the AC, have at it. Like that's a nice night, right? Or you could have 12 transit or sprinter roofs in parallel. Like that's a huge amount, right? That's a ton. Another way is to charge with about 4.6 kilowatts of panels, which is a ton of space. I mean, it's like larger than the size of this room. Most domestic installations on houses are 6 to 10 kilowatts. So that gives you an idea of what type of sizing we're talking about here. And, or you could drive 34.6 hours at 40 amps to charge all 13 of those batteries. So really not viable. Truthfully, use shore power, use a generator. Call it a day, right? The generator is great for off-grid. This is the reason, another argument for the generator, right? It's just realistic in that sense. How many can you carry is another problem that we'll start having, right? So you have 5 here. This is 500 amp hours, right? It can get a little tight if you want to have a lot of batteries. So this is, sometimes the space that you have available can be a consideration when designing your system. So now we're going to talk about system sizing here. So typically, once your usage requirements and then your vehicle requirements, you have all that understood, and it's all install location, it's charge method, you can move on to system sizing, right? I would typically have 2x the amount that you're going to use, mostly so you don't use over 50% of your battery, and you can dip in without really completely depleting the battery or affecting its cycling. The charge systems will define out how fast you can charge. So if it's a 40 amp, it's a 50 amp, it's a 25 amp, those will all change the charge rate. So then that's part of your equation too that you have to think about. And then all of your wiring gauge numbers and their fuses will then depend upon all of the numbers coming out of that. So how, if it's 40 amps, what size fuse do I need? What does this rating have to be? What size wires do I need to be running? All of that will depend on those numbers. So it's a lot easier to design backwards based upon your requirements, and then you'll figure out what wiring and fuses you're going to need by, I guess by deduction in this case, right? When we get to wiring and electrical for automotive, typically I use Anderson connectors for everything. It's really the popular thing that's been used in the overlanding space. They're used in ham radio, they're used in off-road. They're just recommended for just their ease of connection, the total voltage separation that you can have before arcing, and just how easy it is to get those connectors. I mean, my friend came off the plane from Australia, and he had accessories, and he's like, oh, your car already has them. It's connected up, right? Easy, right? That's really, really nice to have that. Another part is to use marine grade parts for a lot of the wiring. You'll see this in the photos of my build. Almost everything is Blue Sea Systems. If they had stock that I could buy, I would personally buy them because I buy so much of their stuff as it is. It's really highly recommended just because they're rated for kind of more difficult environments. I would fuse all major electrical inputs and enter and exits to the system. Any place that really you have power coming in and out, I typically will fuse that, especially if it's a large pipe of something. I'll typically overbuild the wiring gauge. I'll install master kill switches for any places next to the large battery or the inverter for either service or parasitic draw. And I use big bus blocks to handle the distribution because you're going to have a ton of current coming in through there, and you want something that's very easy to connect new connections or do service on your other ones. And so here's a great example of I call it the marine grade wiring party. I have this is a fuse block. I have circuit breaker, big switches, all sorts of stuff.
One question on wiring. Do you have an opinion with regards to negative busing versus chassis ground or running separate?
I'll get to that.
Okay.
Yes, I will be answering that. Wiring size, don't guess. There's calculators out there that do it. If in doubt, always go larger, use copper, don't use aluminum. Still have to be saying that in this day and age. Pure copper strand is really what you should be thinking about. And now you can see the size of the wiring that I'll be showing you in the photos. A single constriction in your current pole can create a lot of heat. So, if some connection gets a little bit loose, all that current is going to then go through one, smaller area. It's going to heat up and you can get a fire. This is the reason it's very important to have larger wiring sizes, very solid connections, so you don't have these problems. Wrong sizing can cause heat, failure, or fire. So just be careful. This is an example of the stuff that I actually use to hook up my battery. One gauge wire. It's large. You can see the cutter that I need for it. I can't actually strip it. That big cutter is to cut it, and then the stripper actually it puts a blade that goes around the copper to pull that sucker off. Stuff is big. It's heavy, but very needed. Fuses and breakers. I almost fuse everything coming in and out, and you'll see that what that looks like in a bit. The predominant fuse types that you're going to see blade fuses for the smaller subsystems. Those are like the ones that you see normally in your car. Those are good for small subsystems. You're going to see fuse terminals. Those are used on top of, usually coaxial on top of an actual battery terminal. And you'll see a photo of what that looks like, but that's for like something coming out where it's meant to go on top of a terminal. So it's meant like this and on top. You have MIDI fuses, which are what most of my fuses in my system are, because they have better heat properties, and it's like a slow trip versus a fast trip, because like breakers will trip very easily on heat, but you have a lot of heat in this environment, right? So MIDI fuses are the ones that are used, and they're almost always called out by the documentation to be using one of them for the very large current areas. Glass fuses are good for very small subsystems. I have a few in my accessory panel, and I'll be showing what that looks like. Fuses protects against shorts. They prevent overcurrent. They prevent fires. I mean, definitely lots of fuses. If in doubt, there's probably a fuse that should go there, right? Breakers are great for other types of subsystems where you can access them, and it might just trip because it's like an external port. There's a few sections that I have that are I don't know what I'm hooking up to it. So I just have a breaker, and if it trips, which is it's like 50 amps. So if it trips, I'm like, oh, okay, I'll just reset it. But it's in a place that I can access, and it's only on a place where I know that I'm physically present when I'm using it. Okay, so here is examples from my build. So here you can see one subsystem that's used actually for the stuff in my engine bay. Okay. This is the MIDI fuse, which it's like a closure on top of the fuse itself, mostly because that's like a water containment thing, so it prevents water from getting as much in. But notice here, this This is actually the cable that goes all the way to the back of my car, including the negative. So both go all the way back. It's like, I don't know, 14 feet of 4-gauge wire on both positive and negative. It's heavy, but it runs all the way to the back of my car. And you can see that's 4-gauge wire. This is 1-gauge wire. This is actually I just made sure the system worked. I just kind of just made sure that this is the smoke test. This made sure that everything was at least functional. But yeah, that's how I actually organized it in here. And so it looks relatively stock in that sense. Organization is key, especially for debugging. I've talked about the importance of master switches. I think that's good. You want to be using a switch that can handle a large, I forgot, it's like a break voltage where the arc voltage is large enough. I think these are like 600 volt arc capable switches, those big red ones that I was showing you. And those are used in marine grade systems just because of the high current that's coming from it and the types of terminals that are used with it. And you can see that here. So these big things here are very, very large. These big red terminals, I mean red switches, and they have 1-gauge wire going up to each of them. Okay. And the one's meant to break for my inverter, and then this one is meant for the main battery. So it'll completely break the battery connection, so I can work on the system without killing myself. Display metering, relatively useful. Know how fast it's charging. Know how much battery capacity you have. Very, very nice to have. There's a shunt that's used to measure the full the current that's actually being used. And on a big system like mine, you have to have a relatively expensive shunt style, so it comes with the actual battery monitor that I have. And I'll show you a picture of what that looks like. It's really big, and what it does is it has a very small type of resistance across that it's calibrated to, and it knows what type of current is coming. And it's always on the, for these, it's always on the negative side. And that actually allows me to check my battery voltage and the charge rating, how much stuff I have in my car, without actually having to be in the back of my car, in the back of my truck, where the system is located. And you can look at what's the draw on your devices. It's really good for diagnostics and knowing where you're at. So let's talk about the final build and assembly. Again, if you're not comfortable with building one of these things, consult or hire an expert. Getting things wrong, you could die. So just be careful. Enclosure and planning, I would say if you have the ability to do a CAD drawing, do that first. That's how I did mine, is I actually mocked up where everything would go first, and then made sure all the pieces fit. I took a lot of measurements. That's how I shrunk that enclosure down to the minimum size that I was able to make it possible. And then I would also build the enclosure out of a non-conducting material like plywood, plastic, or you can do an offset chassis with a powder coat, because the powder coat isn't conductive, but just understand you want to be offset from it. Definitely maybe double or triple check that schematic, make sure all the component data sheets check out on the numbers that they've given you. And if unsure, just assemble it outside of the enclosure, which is what I showed you before, and then put it in the enclosure, such that you don't have to do debug while it's in the enclosure. And then don't connect the battery until after all the components are installed with the master switch, because it's really hard to unconnect the master switch with everything connected. So that's why with the master switch, I can just connect the battery. I can just place the battery in and out of the enclosure with relative ease. And so you can see my planning photos of me kind of mocking it up, making sure everything works. That was a smoke test, and then I immediately took it off after that to make sure stuff wasn't going to explode on me or burn through or whatever. But the basis worked. But it wasn't capable of charging. I was only capable of actually just taking power from it. Here's where I started planning out the enclosure. I drawn it in CAD. I built the enclosure, started checking all the clearances, started putting stuff on the side, just kind of screw, and just went, okay, that looks right. It's organized. Start hooking up all the switches. This ended up being what my build was, which is this guy. So you can see how compact all of that stuff is in there, and how you can still operate it on the switches. This is the accessory one where I can actually power other accessories. This is where the battery comes in, and then this is the front of the panel where I have power that I can access. I have the access to my inverter here, right? Because I was inside the camper shell, it's really covered in marine carpet. It's the same height as the rest of the panels inside my truck. It's a 100 amp hour lithium iron phosphate battery, a red arc system, 100 watt solar panel, and a 1500 watt pure sine inverter. And this is what has been in my car for about a year. I have not had to service it in a year. It just keeps its charge every time I drive. And I've been very happy about it. It's powered my fridge for basically 24/7 for a year. This is the schematic of my system. It's actually relatively simple. It's just taken for the application notes. So you have the solar panel here, you have the starting battery here. That's hooked up to your DC to DC system. Then all of these yellow parts are fuses. Okay, so you can see how many fuses I have. Any place of power coming in and out, large amounts of it, definitely fused. The second battery is here. This is the shunt where I'm actually doing the battery monitor, where it can tell how much energy I'm taking, so it can monitor the current usage. And then these are the bus bars. So you have a bus bar for all the positives and a bus bar for all the negatives. Okay. Right. So relatively simple. This is basically pulled from the application notes. So that should help give you an idea of what that is.
Brief question.
Yeah.
Looking at your positive bus, you've got two, you've got three. Top one obviously is fused. One in the middle I'm curious about.
That's the accessory. That's that gray Anderson power Anderson connector that goes up to a subsystem.
Okay.
Okay. And we can go back to this in the Q&A, but they have 15 minutes before they close. So planning, I started with the size of the inverter and battery, and I worked to the main pivots to arrange everything else. So those are like the big items, and I just pivoted all the other items around it. Arranged, I mostly placed the bus bars at the opposite sides, just because I didn't want to be able to like short it with a screwdriver or something. So that's the way that I try to separate them. I usually put them at opposing points where you can't put an arm in. Well, if it's too small, you can't do it, but you can't put like a screwdriver and just short the entire system and blow up a screwdriver or something. And then, you can cut down on the length of the wires from the large 1 gauge wire if you place it close enough and where the switches are. And just make sure that everything is clean and makes sense, because if you have to service this in the field, I've had to do it once just to, because something worked loose. Then being very organized meant I was just able to look at it, tighten something, and then get back in the car, and it's all done. Okay, so organization is key. And I've shown some of these planning photos before. The tools that you're going to need, right? You're going to need wire crimpers, terminal crimpers, which are needed specifically for kind of the terminal buses. You're going to need very specific types of wire cutters, wire strippers. You need power tools, heat gun for heat shrink. I heat shrink a lot of the connections just for safety, and then all the other associated tools that's meant with building one of these. Some details in the wiring here. So these are actually Anderson connectors at the back, so I can completely disconnect the system if I need to. That's a very important piece. And you can see that here. So that's where that Anderson connector, I can actually just disconnect the system completely from the alternator. That's a MIDI fuse that I was telling you before, and you can see where the negative, I would always run equal length all the way back from the positive and negative terminals. Do not trust the chassis ground. It is not a good ground, okay? You want basically the positive and negative running all the way back, okay? Again, do not trust the chassis ground as a good ground, right? I would always connect it right at the battery, because you don't want any constriction in the system anywhere or anything to second guess. Follow for your wire loom. Follow what the chassis wiring harness does. So on my truck, you can see where it goes. It goes from inside the car in the engine bay, and then it follows down onto the frame near where the frame rails are. Follow that. That's usually a good place, and you can actually attach your cables if you're running it all the way to the back of your car. If you're running it into your car, some other considerations are needed, but it's generally less of a hazardous environment than the outside of your car. I always have a wiring loom over it, just similar to how the OEM does it. Yeah, that part's not as important. Okay, so here's running short on time here. You can see this is the bus block. That's the positive one. That's the negative one. It's really easy to see how they are arranged in here. Generally, you can't short that with like with anything. It's really hard to do it. That's why I've tried to arrange it that way. It's really hard to see because of the contrast. That's the shunt. It's this really big, basically large resistor, a very low, large resistor that has a connection out to a wire out to this guy. And so that gives the ability to monitor what type of current is actually being taken outside of your battery, so it can do a calculation how much battery capacity you have left. Okay. You can see the DC to DC charge, the red arc system right here, and then the inverter, and then the battery. So it helps you get an understanding of keeping everything really organized such that it's easy to work on. Also note that I actually covered up the positive battery terminal, so you can't physically touch. You can touch the negative terminal, right? It's the negative terminal, but you can't touch the positive terminal. I basically put it in a way that you can't get to it, which is good because then you don't have the problem of holding on to both terminals, right? Exterior enclosure, you can see it next to the fridge right here, okay? So you can see about how big it is. I think that's a Dometic 35 watt, 35, I think it's liters, right? I don't remember. But that's a CFX 35, whatever that measure is. And that's actually it inside the truck connected. So it's actually up, it's the same height as the rest of like my drawer and everything else. This is the secondary breaker box that I use to have the power all the way out. And you can see it kind of wired here. And this is the Anderson connector that I use to connect it to that system. And that allows me to control the lights and everything else on the inside. Okay, they're already starting to look. All right, so testing, definitely do a test before you shake down, because when you're off-road, stuff works itself loose. Just make sure it's doing what you think it is. Make sure nothing's going on fire, nothing's worked itself loose. Use nylock nuts wherever you can, just for safety, stuff not working itself loose. That's part of the system shakedown. In the field, so this is me in different national parks using this system. You can see me using the lights and all the other accessories. This is me standing actually above my car on a climb to take a photo, but you can see kind of how the solar panel is arranged. And so this is what fueled for 4 weeks. I was out on the road and never ran it out once. And so that's good for me to see that I designed it the way I thought it would be working. That was really good for me. That's me in Canyonlands and then me in parts of Colorado. So definitely took it to a lot of places, charged well, it was used appropriately. So the lessons learned here, building a system like this can be a rewarding experience. The more custom the need, the more difficult it becomes. And always taking the time to look at your needs and then work backwards is really, really useful. Make sure that you really are thinking about what you're using it for before you go into designing it. It's because it can get really expensive buying all these parts, because my system was like $2,800 parts alone. So, if you can buy an off-the-shelf system like a Goal Zero or something else for really way cheaper, and that's all you need, then use the OTS system, right? There's no shame in using an off-the-shelf system. Sometimes it's a better choice, right? Sometimes simpler is better. I've seen people use these with great success. I mean, yeah, I can't do certain things, but it works. And I think Dometic even has their own system, which is a portable lithium battery that charges off the cigarette lighter. So it's a slower charge, but it's a good battery technology. So it's kind of that in between, like, what is your usage, what is your need, and sometimes keep it simple, Stuart, right? It's just useful. Also, OTS systems are easier to sell, so that's another thing that you should think. You go full custom, it's really hard to resell it. Okay, so I don't think we have much time for Q&A because they're about to kick us out, but thank you everybody for coming.